Okay, guys, let's start after all this setting up of the machinery. Okay, so today we are continuing on the finite state machine discussions, and we are going to extend the model that we have seen, the basic model that we have seen last time, with additional features and make finite state machine usable in a more general context. And so we are going to talk about extended finite state machines, and in particular there is a topic that has been very much studied in the last 10 years or so. It's called hybrid systems. And hybrid system actually is a mathematical formulation that is very much used in a field that now is very, 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 very fancy. It's called cyber physical system. We talk about it in the introduction. So without further ado, let's go on. So the questions for our model is how to represent a system that we want to analyze for systematic analysis, and so that a computer program can manipulate that model. Okay, so they can optimize it, it can simulate it, it can change it. Now, the other thing is that how you model the environment in which the model is going to be inserted, and also how you want to compose different models to build a bigger one. It's like a Lego block approach, right? So you take different pieces, you want to piece them together so that you get a bigger thing, right? So now, in general, this one is, as I said, is a general concept. When you model something, you can do it what is called at the lowest level. So we also say you model the system flat, right? In general, when you model a system flat, you have way too many, if it is large, way too many equations, way too many things to worry about. So most of us think in abstract terms. So we try to get away things, right? Now there are two kinds of simplification that take place. One simplification is abstractions. You throw away things that you don't want to see. So in some sense you aggregate parts of your model so that you can handle it. The other way is to think about the whole as being composed by a number of smaller parts that you plug together. So this one is composition, is a composition operation. Now, composition is a basic concept also in computer science, in algorithms, whatever field you want to think about. This notion of building bigger things by aggregating stuff is a general one. So now the point is that what are the rules according to which you put them together? And that's what makes the stuff interesting and not obvious. So let's get this out of the way. Plop. Okay. Now, recall the finite state machine notation. We have states that are labeled with a name and are encoded in a particular form. Then you have a guard that tells you when you can take a transition on the finite state machine. Corresponding to that transition, there is a setting of an output. And so the way in which we indicate that, we say guard/action. We also have to give an initial state. So the initial state, we have to indicate it somehow. I told you that in general, in the finite state machine notation, you put a double circle to indicate where you start. Okay, and then of course you have self-loop, which means that under a particular set of conditions, then you stay in the same state. So you do an action, and the action is stay there, right? So since it is a transition, staying there in this model, it means that during that transition you can output something, right? So you keep on looping, but maybe that something changes and is the output during this loop. Okay. Now, garage counter example, we already did this. We have a model that has m states, where m is the total number of positions that are available in the garage. And so it's a pretty stupid finite state machine, if you like. It's all the same, right? So m times repetition of the same thing. So what would you immediately think about simplifying this one? Does anyone have a wild idea about how you can simplify this continuous repetition of the same thing? Exactly. So what you could do is that this one is essentially a counter, right? It counts up and counts down, right? And so at every transition, you output something, but that is always the same actions. So why don't I reduce all of this just with one state, right? And this one state is characterized by a self loop, which outputs the counter plus one, right? And so this is a way of implementing a counter. It's just a single state. And so that's the way it goes. Here it goes, right? And so there are two self loops. One which says, okay, the counter goes up by one, so there is a new car coming in. And one goes the other direction, a car leaves, so you have a self loop, and the count is decreased by one. Now, notice that the output at this point in time is no longer a pure signal. It's an integer, right? Which corresponds to 1, 2, 3, 4, 5, n. And so this one, strictly speaking, is not a pure finite state machine, but a finite state machine whose output is a natural number, okay? So, but it simplifies the notation of a finite state machine greatly. So what you do is that you encode that information that the state is changing, right? Always the same, goes up and goes down, etc., is captured by the self loop and by the variable that is assigned with a transition. And so that variable grows by one or decreases by one, and that takes into account all what we said. Now, notice that the condition under which you take a transition, a self loop, contains the variable that you have inserted, the count variable. And so if count is larger than 1, then you can decrease. If count is equal to 0, then nothing, it doesn't make sense to decrease because it's an infeasible situation. A car cannot live in a place where there is no car, right? So that is what this representation does. And so the output, instead of being a pure signal, so absent present, at this point in time is a natural number. Okay. Now, the interesting point is that what is the size of a state space? Because the state space before was m, and this time it seems just 1, right? But remember that you have also to take into consideration the space that is indexed by the output variable. So the state space is still the same. This one is a shorthand notation to avoid to say stupid things. Okay. Now, the general notation then for extended state machines is the fact that the outputs can be variables. Okay, so that's it. Instead of being pure signals, they become variables. So they can take real numbers, they can take values on the set of natural, whatever you want. So this is the extension of the notation of the finite state machine. And so there is a guard, there is an output action, and a set action. The set action means set the variable to a value. That before didn't have sense because didn't make sense because we had a pure signal. So the fact 0, 1 is all you need to say. Okay? Okay, so that's the extended finite state machine. It's interesting to find out that if you take values, the variable take value on a finite set, then this is still a finite state machine. Remember, 0 to m, we know, we already had expanded into m states, so we know that it is a finite state machine. Assume that the set action involves variables that are in the real, okay, so the real numbers. Can you claim that, so you have these states, but the output, instead of taking values in a finite set, takes value in a real, okay, in the set of real numbers. Is that a finite state system or not, according to you? No, right, it's not. It's no longer, and so in fact, it's very interesting because certain questions about the behavior of a finite state machine, when you have these outputs that take value on the reals, cannot be decided. So you cannot say, yes, it works, no, it doesn't work. So it's an undecidable problem. So incredible, right? So you set a variable in the reals, and the entire complexity of the game changes dramatically. It is no longer a finite state system. But it's very convenient to model things, right? So then you can do, which trick can you do? Well, you put a bound of the real, it cannot be larger than 200, say, and then you discretize, and all of a sudden the thing that was not finite becomes finite, but because you start throwing away stuff, right? And so there are tricks in which you can still answer questions and things like that, but you have to do an additional simplification. Now, let me give you a realistic example of what the controller of the traffic light looks like. Okay? Now, this traffic light, can you tell me what it's saying? What is the operation of it? So read the model and tell me what this traffic light is supposed to do. Traffic light controller is supposed to do. So what do we see? We see pure signal, which is red, yellow, and green, and that's, of course, is either red or yellow or green. It cannot be partially yellow, partially green, or something like that. So that is a pure signal. We have pedestrian. Pedestrian means there is a guy who wants to cross the street. And so also that there is not. Right? So that's as simple as that. And we have a count which takes value on a discrete set. So it is still a finite state system. And this set is 0, 1, 2, 3, 4, 5, up to 60. So if you look at that, so we start from an initial state and assume that the initial state is red, right? What does this say? Well, it says that I'm sitting on the red by incrementing the count, right? So count plus 1. Count is 0, so it becomes 1, it becomes 2, it becomes 3, it becomes 4, so it stays red. Now, when the count is larger or equal than 60, I take the transition and I go to green. And I reset the counter. So what is this counter? What does it represent? Time. It's time, right? It's how long it's going. So assume that one count is 1 second. So it means it stays there for 1 minute, right, in the red. And when the count is larger than 1 minute, then it goes to green, but it resets the counter. Why? Because now same thing. So I'm going to green, and so I have to decide when I'm going to go from green to yellow. Now, what happens there? So if count, you say, as long as counter is less than 60, I count plus 1. Now, if I see a pedestrian that is there, and count is less than 60, then I do pending, and I increment counter by 1. If the pedestrian and counter is larger than 60, then I go to the yellow signal, and then eventually I move to the red. Now, what this says is that you don't want to turn the signal green in the other direction if there is a pedestrian there, right? So you don't want it to be run over. So, okay, so this is what this thing does, and essentially stays into the green, red, yes?
As per this model, how can we ever have count greater than
because there may be an error, for example. In this situation, you can start with the counter which is larger than 60.
But we always have that initial state where count is 0, right?
Because I assume that because I told you that was the initial state. That could have been another state, right? In principle. So, and you always put larger or equal than just to make this sure, right? So, in fact, if I start from there and there, it can never go above, right? But there could be sometimes you put that too, also because there may be a misreading of the sensors, right? And so it should be 60, but it's 61, right? So you don't want to stay there forever, right? So you say, as long as it's larger than 60, get out of it, right? Okay. So when does the reaction occur? So we already said when the count reaches a specific value, then it takes a transition. Now, the fact that it takes a transition, it depends on two things, right? One is the pedestrian is there or not, and the second one is the time has elapsed to 60 or not. So of course, these are exogenous variables, are things that are not under the control of the system itself, so the inputs come from somewhere else. So the condition under which you move are given by the environment. Now notice that we said that there is this counter, right? 1, 2, 3, 4, 5, and all of that, right? So, which means that this model is time triggered. So you take a transition if the counter has a particular value. So it's time triggered. So when, for example, a pedestrian gets in, it's not necessarily true that I do immediately an action, right? So I have to wait for when the counter gets upgraded. Okay, now, if indeed you take this finite state machine, there is no counter there, so it's input and output, then the semantics of the finite state machine is intrinsically reactive, which means it's event triggering. So the transition takes place when something changes in the environment, the guard becomes true, and you take the transition. Okay? So in fact, if you have, for example, a node with 22 inputs, right, the semantic of a pure finite state machine, not time triggered, says that whenever any of these guys changes its value, I take a transition. Okay? Now, if I had a synchronous implementation, all of them have to change, right? And so that is the basic difference between event triggered, if you like, and synchronous time triggered. Okay. Now, suppose that x and y are discrete and pure signals, right? So this S1, the condition is not x, right? So when does this transition occurs? Well, the point is that it can never occur, right? Because you can take the transition when x is present, but the guard says, no, you cannot go. When the guard says you can go, there is nothing in the input, so nothing you can do, right? So this one is a kind of contradictory finite state machine in the sense that it will never move, so always stays in S1. So when the environment triggers a reaction and X is absent, if this is a complete event trigger model, then the transition will never be taken, because in order to be taken, X has not to be there, but the reaction occurs when X is there. So you don't move, nothing happens. Okay. Now, let's get back to our wonderful traffic light, and then the traffic light controller, we already said, is a time triggered because there is a counter and the transition are guarded by the value of the counter. Okay, so this time trigger model, we assume that 1 to 60 means 1 minute, so every tick is 1 second. Now, notice immediately that the same mathematical characteristic of this model occurs when the unit of time can be hours, right, in principle. So there is a indicization in terms of a unit of measure that takes place, which is also a nice feature of these abstract models, that you can make them parameterized with respect to the variables that you want to set. Yeah. Come on, Zik.
What if you're on green and there's no pedestrian? I mean, pedestrian is 0 always.
Then you stay green. So, which means that there is no pedestrian that is trying to cross on the other side.
Yeah, but then that self transition doesn't have, like, it has only count less than 60, so then that won't be true, right?
Yeah, but there is a transition goes to yellow. You see that? Pedestrian count larger than 0.
Yeah, I'm not saying something pedestrian always is 0.
No, you're right. There is a mistake. Should be pedestrian and count larger than or equal to 0. You go to yellow. So instead of and, because otherwise you can never take a transition, yeah. And the counter can go up. So this is a mistake. Thank you for pointing out. So let me make sure that I'm saying the right thing. Count pedestrian count. So if pedestrian is not there, you stay there, right? Count larger than 60, so if pedestrian is not there, nothing you can do. So it's inconsistent. So we'll fix it. Thank you for pointing it out. Okay, so now I told you about this wonderful thing that are called hybrid systems. What are hybrid systems? Hybrid systems are models that combine a finite state machine with continuous evolution. It's a combination of the two. Now, in what sense is a combination of the two? Assume that I'm a robot, right? So I'm set forward, right, of this toy that you give to children, right? And the robot goes like this, boom, hits something, and then what happens? Remember, I mean, the toy, it goes that way, right? So what happens is that when something happens, so when the continuous trajectory hits the wall, you change mode, right? So instead of going forward, you go backward, right? So what does this mean? That the guard is determined by the evolution of the mechanical system, in this particular case, by kinematic in particular. And so there is a differential equation that is taking place. And when the variable that is described by this differential equation reaches a value or a threshold, then you jump state. You change the mode of operation, right? So that is the general model, if you like, of the hybrid system. So it's a combination of a continuous evolution and a discrete evolution. Now, if the robot goes like this and finds nothing in front of him, that transition is never enabled, right? And so, which means that you're always going to stay in that state, and the continuous system will continue its evolution. Now, by the same token, if you are driving a car, then you have, remember, once in a while there is a signal that comes up, right? A sensor that says, oh, red, 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 stop, 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 do something, right? But you hope that this will not happen, right? Because there's a bad signal. So if the behavior is nice, if you like, then I will continue driving my car forever, right? So I don't need to change state. So the change of state corresponds to a triggering event that makes the differential equation change its evolution radically, right? And in fact, this, for example, boom, it does that, resets its initial state, and stays into that node until some boundary is hit, right? Now, what that set where we stay there and we don't change is called the invariant set. So the set where nothing changes. So I keep the differential equation is what takes place and nothing else. So it's invariant with respect to the finite state machine. So what do we use this for? So this is pretty. Someone had a question? No. I heard the voice. Okay. So, all right. So where do hybrid systems arise? Digital controller of physical plane. The digital controller of physical plane was the example of a robot, right? Hit the wall, then there is the digital controller that sets the motion in reverse. Thermostat is one point in time. We saw it already last time, the model of finite state machine model of a thermostat. But the temperature, we say if temperature this and that, then do that. Now, if we want to model also the environment, then the temperature is a continuous variable, right? So it evolves. And so the action of the controller takes place only when temperature hits a threshold. Aircraft autopilot. So that's something that intelligent cruise control in cars. Or phased operation of natural phenomena, like for example we'll see. I'll give you a concrete example which is actually used in designing controller for engines in cars. Bouncing ball, so if you have a ball and you let it drop, right? So when it hits the ground, then it changes its direction, it deforms and changes its direction. So that can be represented as a hybrid system. Biological cell growth, the same thing. So now you can also model what is called multi-agent system. So for example, if you have multiple planes, right? So you have multiple planes, air traffic controller. How does it work? So you have these planes coming in, and then at a certain point, so it's continuous differential equation, and then you see that there is a collision occurring potentially. So as soon as you see that the condition for a collision happens, you change the control, and you tell one guy to go up, right? And so that is a discrete change caused by a control action due to a triggering event, which is a continuous system. Interacting robots, so if you want to have 5 robots that are playing soccer, then they have to coordinate, right? So they have to tell each other what to do. In this particular case, then you have the overall controller, a supervisory control that tells each of the robot what they need to do. And then they take the feedback from whatever happens on the field, and then they change their operation. Okay, so automotive. Yes?
What is the difference between embedded system, hybrid system, and cyber physical system?
Hey, good question. So embedded systems is anything that has a sensor actuator and a control and a computing platform in it, right? So it is independent of a mathematical model that you use to represent it. Right? Hybrid system is whatever is a combination of two different incompatible model of computation. So finite state machine, continuous system is a hybrid system. Now, a hybrid system may not even have a controller, nor a sensor, nor an actuator. In fact, we see the engine control that goes up and down, up and down, up and down. And actually, the engine itself is modeled like a hybrid system with no controller. So that is not an embedded system per se, right? It's a mechanical system. And then a cyber physical system is exactly the same as hybrid system plus embedded system. So it's a combination of the two, except that the only difference that you see in cyber physical system is the conceptual view that you have multiple of these. So there is a network system, but that's not. But the other important thing is the fact that you are co-designing the controller, so the embedded system, with the physical plant. Okay, so that's a real most serious thing. But remember that if you remember my first class, I told you that same thing get renamed for political reasons, right? Political reasons is that you want more money, you want to put the emphasis on a particular aspect, you want to go on newspapers, you want the industry to get excited about. Then you may ask, what is the difference between Internet of Things and cyber physical system? None. But yet you have $2 gazillion in IoT, you have $2 gazillion in CPS, and everybody's happy, right? Okay. But it's a nice name, Internet of Things. Sounds good. And then now there is Internet of Everything, in which you put the human in the loop, right? And so guys, don't laugh. This is your life, right? It's going to be your life. So believe me, after 40 years, I can guarantee you that that's going to happen all the time. So once in a while, there is a real major change of paradigm. But for example, if you talk about swarm systems, then it's a different story. So could be a swarm system, could be seen. What is a swarm system? By the word swarm, it means that there are gazillion devices, right, or gazillion things that you need to play with, right? You need to control, you need to verify, you need to use, right? So the difference between the Internet of Things and the swarm system is the fact that the Internet of Things, in principle, you could control every piece of it. There is no intrinsic notion of redundancy or things like that. In the swarm, like the swarm of bees, of ants, all of these other characteristics are present. So in some sense, swarm systems are an evolution of Internet of Things, cyber physical system, wireless sensor network, all evolution, boom, swarm systems. But it's always this continuous kind of trying to find what we can innovate, right, to get to a new market, to make more money, or to write more papers, same story, right, different measure, same thing. So in academia, you write more papers. In industry, you make more money, but you define new fields to do this kind of stuff. Okay, so now, this one is the representation of what happens in a car seen as a global object. So, and this one is also called a modal model in the sense that each of the nodes corresponds to a mode of operation of the car, so a way of operating. So now, for example, you are in the stop state, which means N is the number of the revolution of the engine, and F is the torque that is produced by the engine. So if the car is parked and is stopped, it doesn't move, so no revolutions, and it doesn't generate torque because it doesn't move. Now, at the startup, what do? You put the key in, and you turn the key. Now, what happens with respect to the stop mode, there is only one thing that happens, is that the number of revolution of the engine is whatever, right? So according to how much you push the accelerator pedal, but you don't start moving right away, right? So you're in idle and then you have to move somewhere, right? To make the car go. So that is the startup. Now then, these other 7 states are corresponding to the following. Idle. Idle means that you are going at the minimum amount of revolutions in the engine that prevents the car from stopping. Right? So when you are there and you are not, the gear is not engaged. For example, you are waiting at a traffic light. That is when you have the idle. So there is no force, no torque being transmitted to the drivetrain, but you don't want the engine to stop. And so there is a minimum number of revolutions that will prevent your engine from stopping. Now, most modern cars, to save fuel, you actually turn off the engine. Right? And then you restart when you press the accelerator pedal. Right? That's another mode that is not captured here. It will make the finite state machine bigger. The RPM tracking, it means that there is the guy who is controlling the car and is sitting there and he has a Ferrari and he wants to start really fast when the signal becomes green. And so it does boom, boom, boom. That's RPM tracking. Okay? So your gas pedal is telling the engine to go up and down in terms of number of turns, but the car doesn't move. Okay? So it's another way of operation. Notice that there is a reason why you want to decompose the behavior of the car in this way, because for every region of operation there is a different controller. And so this is a way of making the problem simpler to solve. Now, I want you to think about what is a fast positive force transient. Now, have you ever, say, you are in a race with your friend at the traffic light, right? So what you want to do is you want to accelerate the car maximally. You want to get, wham, right? So that is what is called fast positive force transient, which means I really want to go from 0 to 100 in 5 seconds, right? That is a measure that give you for the car. You say, how long does it take to go from 0 km per hour to 100 km per hour? They use this mode. So fastest possible acceleration. Now notice that this is corresponding to g dot larger than 0. G is the movement of the gas pedal. So if the velocity, right, is larger than 0, means that your gas pedal goes down, right? So it goes like this. So your foot is pushing the gas pedal. Now you have constraints. So the two constraints are the fact that the fuel consumed must be less than a particular amount, so you don't go infinite revolution per minute. And the other thing that is very important is the comfort. So if you have, for example, a Ferrari, nobody cares about the comfort. So if you accelerate, or Tesla for that matter, so when you do in fast positive force transient, you are boom, like this, which is not pleasant, but some people is exciting, right? But you can have your neck snapped, right? So that is that D larger than D mean. In this particular case, D mean is absolutely 0, right? In the normal cars, you don't want to be killed, right? So that's the situation there. Now, the fast negative force transient is when you take your foot off the pedal, right? And so you want the car to decrease the number of revolution as fast as possible. And in fact, when you hear about the engine which acts as a brake is when you do that operation. So the controller will take your engine essentially to try to go to 0 revolution per second, because then it acts as a brake. And so the drive train is actually pushing the engine. So the engine is not giving torque to the drivetrain, it's the opposite. So by doing that, you slow down the movement of the car. Then speed tracking is when you have the cruise control. And idle and transmission on is when you leave. For example, if you have an automatic gear shift, right, and you're sitting at your traffic light, that's what happens, right? So you're idle, but the transmission is on, right? And in fact, if you are on I don't know, the very nicely designed cars, if you're sitting on a slope, right, turning like this, and you have a red traffic light, San Francisco, so boom, you're sitting there, then it's kind of tricky, right, because you have to push the brake pedal, otherwise you go back, right? But these modern cars, if you're sitting there idle like this, it will generate enough torque to keep you stable, right? You don't go back. So you don't need to use your brake pedal. It's not an easy problem to solve, but that is the controller that you can put in that position. So this is a way of specifying the way in which the car operation can be seen, right? And this is a specification because it will tell you what to do in each of these states, and you will have to design a controller that does exactly what is written in these nodes. Okay? This is a hybrid system. Why? Because the guards are related to the speed of the pedal, are related to the speed of the car, are related to the number of the revolution of the car. So it's a hybrid system. There is a mechanical system that evolves and triggers action from a control point of view. So that is one use of hybrid system. Another use is actually to describe the operation of an engine and the drive line and the manifold. Okay, so this is a diagram of a very simplified diagram of the car, in which you have a manifold. The manifold is the pipe that takes you from the valve into the engine and modulate the amount of air that gets in, okay, into the car. And so, for example, when you press the accelerator pedal, you open the throttle, so you increase the amount of air that gets into the car. And that is the basic mechanism according to which you accelerate the car. The engine subsystem, so there is an engine. The engine is, the normal combustion engine. You have pistons, and you have fuel, and you have to inject the fuel into the piston, and you have to give it a spark to make it ignite, right? So in diesel, it's not that way because the pressure is enough, so you don't need the sparks. But for gasoline, you do need the spark. Now, the combination of the spark timing, the injection, and the air that comes in gives you a torque that then gets given to the drive line. The drive line is whatever is attached to the engine, right? It's what makes your car go. So it is what connects to the wheels, right? So that's the drive line. Now, the operation of a drive line is a purely mechanical system, so it turns and the wheel turn and you have to overcome inertia and all that kind of stuff. It's a purely mechanical system. The manifold is a throttle, is a valve that continuously moves from a 0 position to a 90-degree position, and that is also a continuous system, right? So these two parts are described by ordinary differential equation. Now, how about the engine itself? So, well, the engine itself, you can model it at a very low level of details by looking at the actual movement of the piston up and down and about what happens inside the piston. So you have to model, for example, the process, the combustion process. The combustion process is like an explosion, right? So there is an explosion and it gives the torque to the piston. So if you want to, you can solve the explosion equations, which actually are very difficult to represent and are described by a large set of partial differential equations. Now, do you really care about it, or is too much? Now, what do you really care to find out? Well, essentially, what you want to know is how much torque is my engine going to deliver to the drivetrain, right? If you have a 4-cylinder car, how many cylinders give you torque on the drive line? Did you ever think about it? 2, right? And why? Because the 2-cylinder go up, right? Then there is a ignition, go down, and the other 2 are actually taken by the first two. So, and what do? They expand, right, when the explosion occurs, and then they are pushed back by the other two, and what do when they do this? They push away the exhaust gas, right, and that's what comes out of your back, right? And so there are two pistons at all times being active, right, and correspond to the... Now, when this thing occurs, ideally, this explosion occurs when the torque is being generated. It's so-called the expansion phase. It's only one cycle of the 4 cycle. Only one cycle where you get torque, right, for every single cylinder. Out of 4 phases, just one. Now, the other ones correspond, when do you change the phase, right? So you go compression, boom, expansion, exhaust, aspiration, compression, explosion, throw out the bad stuff, and suck in the new gas, right? So 4 phases, right? So that's what we need to know, is the 4 phases. Each phase is characterized by the fact that the piston reaches its topmost position. It's called dead center. So a piston goes up, changes phases, goes down, change phases, goes up, change phases, goes down. So 4 states. For each cylinder, there are 4 states, which correspond to the fact I'm going up, I'm going down, I'm pushing away the bad stuff, I'm taking in the good stuff. 4 states. So I can use a finite state machine. Now, what is the trigger that tells me when I need to change the state, right? Is the reaching of the topmost position, right? Now, how can I see when I reach the topmost position? What is the law that I have to look at to find out when I get to the topmost position? What is the dependency? So what makes me go there? Well, it is the amount of speed, if you like, the amount of motion that I get from the drive line, right? The drive line is, have you ever seen a drive line for a car? It's like this. And this corresponds to where the piston comes in, and it turns like this. So actually, the drive line pushes the piston up and down, right? So when you don't get the strength explosion, you get pushed by the drive line, right? So what you need to know is you need to solve the motion of the drive line to figure out when the piston is going to reach the topmost. So, which means that the finite state machine is guarded by the evolution of the differential equation that describes the movement of the drive line. Okay? So it's a hybrid system. There are states, the 4 states, and the condition under which you go from which state to the next is dictated by the drive line. And so, okay. Yeah. And that is also correct. In some sense, what you see is actually a feedback, right? A feedback loop. So I control you and you control me, right? So my position, the position of the drive line is due to the fact that I give you force, but my movement is due to you, right? And so that is the beauty. Otherwise, it wouldn't be a hybrid system, right? It has to be all together, right? So because it would, if it were decoupled, it would be nice, right? So the piston goes up and down and this thing does its own thing, but it ain't happening, right? So they are tied together because they are, on the same mechanical component, so essentially, right? They are connected, right? And this is the interesting thing, right? That comes up, right?
Mathematically, that's the fact that it's a differential equation.
Right, but it's a differential equation where the input comes from the explosion, right? The torque that I give to the drive line, but also to determine when I determine when the thing gets the push, right, is by the differential equation. So the finite state machine has an input into the differential equation, and the differential equation has an input into the finite state machine because it tells when changes state, right? Okay. So that is, in my opinion, is a really nice thing. Now, not because we did it like 15 years ago. This one of the first papers in which you actually link hybrid system to controller in cars. And right now, most of the controllers are designed this way, so pretty good. So we have a continuous system that is the intake manifold, that is the position, plus alpha is the angle that is impacting the cylinders. The cylinders receive the injection actuators and the ignition actuators. They go to the crankshaft. There is a clutch, which goes to the primary drive line. Then there is a secondary drive line, and you get to the motion of the car. That's the entire car, right there. That's the powertrain of the car. Okay, now, there is something interesting that I would like to point out, because we talk about the finite state machine and the position of the mechanical system. But there are two other things that we need to take into consideration, right? To figure out how much torque do I get? What will be the dependency, the amount of torque that I get? The force that I get on the piston depends on what? I know that there are some mechie here, so you should know. Think about it. So when you push the accelerator pedal, the car goes faster, right? So which means there is more torque. And what happens when you push the accelerator pedal? The angle, the intake manifold changes its pressure. So which means that exactly right. So what happens is that the dependency on the amount of torque is on the mix that comes into the cylinder. So there is a rich mix, means a lot of gas in there, and so what happens when you give a spark, boom, right? It gets a lot of force, right? And so the speed increases, so you absorb more stuff, and so you go faster and faster and faster, right? And so that is exactly right, okay? Now, there is another variable. So we know now that it depends on how much fuel gets into the piston. There is another variable, which is, yes. Well, yes, but that is given, right? Right, timing. So you are a mechie. No, you like cars. Yes, okay. So is the time of ignition, right? So why is that? Because
so you say the piston's here and then you have combustion, you have a lot more force. But if the piston's already on its way down and you have combustion, then it's not really going to give it that amount of force.
Exactly. So what happens is that in the old times, you couldn't do that, right? In the old times, it was all deterministic, all mechanic, right? So you couldn't get what is called spark advance. So you cannot control the time of ignition, right? So the time of ignition is a controlling variable. So suppose that you are in the situation where you took your foot off the pedal because you want to stop the car or you want to decrease the speed of the car. Remember that the decision how much gas is going to go into the piston because of the 4 phases has been taken long ago, right? 2 phases before. And so now you have all this gas, right? And you don't want to create too much force because you are accelerating and you don't want to accelerate. So how do you do the trick? You say, aha, this guy goes up. I don't give a spark. I wait this coming down because the other guys are pulling it down. And I give the spark when I'm halfway through. So the push that I get is much smaller, right? Because the chamber where I'm going to take the expansion is already expanded. So that's a trick. And that is called spark delay, right? Now, can I do also the opposite? Can I also put the spark before I reach the topmost thing? And why should I do that? The answer is yes, of course. But why should I do that? Now, why am I telling you this? Because I want you to think what goes into the process of modeling a problem, an engineering problem, into a mathematical model, okay, in the most abstract sense. Because believe me, no one in the world was using finite state machines to represent the behavior of the engine, while if you think along these lines that we are thinking now, is the process that allows you to build a finite state machine that represents faithfully the engine for your purposes, which is controlling the motion of the car. So why do you want to put the spark before you reach the topmost? Any idea? No, that was a delay. That we already discussed. If you before you actually, so what happens is that you get what? You start the combustion process before you hit this point. So what could it happen?
Well, so if the piston is trying to move up and you have the combustion that's before
Right,
down,
right. Right, for example, we'll get to that. But this is a side effect, which is a negative side effect if you do it too much. And this is called knocking. Have you ever heard your engine, I mean the old engines, when it clink, 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 that's bad, right? And so essentially it's when you are in third gear and you're going 1 kilometer per hour, when you clank, 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 and the thing is that the gas is actually auto-combusting, right? So it's the spark, it doesn't do anything, and so you get the spark in the wrong moment, and you destroy your engine, okay? Not good. But it could be positive, and why? Because as any dynamical system, right, any dynamical system, there is delays, right? So there are things that occurs that need time to develop, right? So the combustion process is a physical process. It does take time, right, to ignite. I mean, time we're talking about in the order of milliseconds, but it does take time. So if I give the spark just at the right moment, I actually maximize, because I start the combustion process already. So when I'm at the topmost, I actually get the maximum expansion in the shortest possible time, because I already started generating this nonlinear phenomenon that is the ignition, right? So remember I told you we had 4 states. Now with the spark advance, can I use 4 states, or I need to be more clever? I need to put more stuff in it. Because now there is another variable that you may need to represent, which is the advance, right? Positive or negative. So it's another 0, 1 variable that I need to put in. And so the number of states has to go up. And so let's see how it can be done. So this is a cylinder that are sitting there with the quantity of gasoline comes in, the spark. Hello? Okay, this intake, compression, expansion, exhaust thing, we already discussed it. This is a mathematical model now, and that final state machine that you see there is the spark and the amount of, and the movement of the drive line that takes you to the various positions, and then the output is the command of what the torque will look like. Now, here it is. That's a finite state machine. No more 4 states, but if you look at it, there are 6 states. And the 6 states correspond to the fact if I anticipate the spark or I delay the spark. Okay, now, you could do a continuum between delay and spark, but nobody does it. Too complicated. So there are only 2 states, either anticipate or delay. End of story, right? And so that's the reason why 6 states are good enough. So the H up there is exhaust phase. Then if you reach the dead top center, you move from H to I, which is the intake. The intake, after you reach the next dead center, goes to BS, right? BS is not bullshitting, but is actually the phase in which you are ready to take the decision of igniting, not igniting, what to ignite, and so on. So if the spark comes in, you go B to S and spark advance, which is PA. If you get this one is negative advance, right? And if if you don't take no advance nor delay, you go directly to the explosion phase, right? So these 2 different paths corresponds to the decision, 3 paths from one state to the next, depend on the decision that you are taking for the advance in the spark or delay of the spark. So this one will be the path. Unfortunately, red doesn't read very well, but what is written there, it says that this occurs, the spark occurs in anticipation. Then you go to the state PA. Then you move to the expansion phase, which is the one which is characterized by AS. Now, if indeed you delay a spark, you take this path, right? So according to the fact that you take the spark early or later, you do a different path in the finite state machine. The composition of all of this is a hybrid model for the engine. Now, this one is accurate. This one is as accurate as you can get, this model. Yet, we don't look at the explosion of the mix in the pistons. We don't look at the dynamic movement of a piston. We don't describe that movement. It's no use, right? We can abstract it away. We cannot abstract away the behavior of the drive line because that dictates where the pistons are going to be, so I cannot move them out. So this one is a process that you follow to have a complicated physical phenomenon and try to find what matters, right? And throw away the unnecessary details, right? And yet be accurate enough that you can take good decisions on the control action, which is when you give a spark, okay? Now, you know what people did before using this finite state machine model? They use average values for everything, right? So instead of taking up, down, we took the average to decide what control action to take. And of course, you had knocking, you had all kind of bad stuff, right? So the fact that you introduce a finite state machine is increasing complexity a little bit, but it gives you so much more, right? And of course, nobody was trying to solve all the equations with partial differential equation, ordinary differential equation, all that kind of stuff. No one has ever tried. Okay? So this is again, what I would like you guys to come out from an embedded system design class is the thinking process that goes into designing these things. That is the modeling process, and the modeling process implies that you have to find mathematical expressions for the physical phenomenon that you are trying to master. You must use a mathematical model for the actions that you are going to take on the system, and then you have to analyze the mathematical model, and then finally you move to implementation. If you have done things right, if you have used the right tools and all of that, you can even do all the nitty-gritty details of the implementation automatically by generating the actual code that goes into the controllers. Now, anticipation. By the weekend, your TAs will generate, together with me, we have spent all this morning, the decision on how the project is going to look like, and this is it. So I want you to apply this particular process to an application of your choice. But I also want you to think about the general methodology about designing embedded system. So we are going to give you a given platform. So it's something that you cannot get away from. You have to use pieces out of a library. So you will have available sensors with their characterization. You are going to have available a computing platform, which will be Arduino boards or I always remember electric imp, and these are the computing parts of the platform, and then you are going to have a set of actuators. This is what's given to you, so it's like a Lego box. Now build your own building. Okay, so find me an application using this set of stuff, and the best application will get a nice prize. Bottle of Italian wine. Yeah, together with the A+, right? Okay. And so people don't drink wine, we'll discuss. And a bottle of Coke, right? Maybe not so great, but... So I volunteer the prize for the wine, not for the Coke. Okay, now, so I want you to think about the application, how you model the application, how you choose the components, how you map the mathematical thinking onto the platform, and I want you to verify that what you do is actually correct before you do it, right? And so we'll ask you to use either Simulink or LabVIEW. Both of these things will generate code. They are capable of generating code, so they are capable of, making your platform do what you want without doing the low-level coding. But if you want to do the low-level coding, be my guest. You will see that it's much more likely that you are going to make mistakes, but it's also more likely that you are going to find a better implementation. Trade-off, right? Okay. Now, so coming back. Among all the possible hybrid systems where there is this differential equation that governs the mechanical part of the system or the electrical part of the system, for example, there is another application where this hybrid behavior shows up in spades, and is the power distribution system in airplanes. You know, airplanes are little electrical power plant, right? So how do you get electricity in the plane to make the movies go and all of that? Any idea? What? Yes. Yes, as an engine is a secondary drive line, right? So the equivalent of a secondary drive line that we see in cars is the same thing. So there are turbines, right, that generate electricity, right? So this electricity are motors, right? And so they get delivered to motors. So there are generators that have to deliver electricity to the motor. Now, what are the secondary loads? Yes, movies and all that, but also what else do you get with electricity in your plane? Well, if you look at the broader right, to make the plane go up or down, they had the pedals, right? So the people were pushing on the pedal and flap will come up and so on. Do you think it's the same way now? No. And so how do you, when you land, you see this thing coming up and making a lot of noise. And then if you look underneath it, you see a lot of hydraulic crap in there. So who activates this stuff, right? Engines, right? Electric motors that flip this thing up and down, right? So you have to have the generators deliver this thing to the... So if by any chance the generator breaks, what happens? Boom, right? And it's not that you don't see your movies, right? You go down because you can't do anything to the plane. There is no mechanical system. There is all electric. So what do you have to think about? You have to give redundancy, right? So you've got to have at least two motors, right? Two generators in the plane. But now, so you have the right generator and the left generator. And you have buses that take the power to the appropriate part of your system. Now, suppose, it may very well happen that one of the generators blows up, right? Very possible. So what happens? Oh my God, right? Half of the plane goes down. No. What happens is that the buses can be crossed. So this poor generator that had to do only the left part gets to do the right part as well. Now what happens when you have a generator that has to deal with too many loads? Blah, right? So no good because boom, again, right? So think about it. What can you do? So the thing is that you want to keep the thing going, right? Who cares about the movies, right? So what you do is that you shut down the things that are not as important as the fundamental thing. So you keep that going, right? And now isn't that a controller? Is that a set of discrete action? What are the discrete actions? This guy is blown up. I need to bridge the buses. What is that? Discrete variable, right? So it's called a contactor. It's a huge switch, right? It's a ka-chonk, right? It does like this. Seriously speaking, it's that ka-chonk. Horrible noise. So that, boom. And then you have to take out the loads, right? And what do you need to do to take out the loads? Bleep, you open other contactors, right? So you close this, you open that. So that is a hybrid system, right? So this is a discrete, there is a number of states, this is down, this is up, combination 2 to the n of these switches up and down, and this is the number of states. And you switch from one state to the next if something happens, right? Okay, so that's it. So this particular modeling strategy is very, very effective. Now, unfortunately, if you want to demonstrate something, if you want to say, okay, under all possible circumstances, my design is correct, can't do that. Why? Because it's no more a finite state system. It's an infinite state system, and a combination of ordinary differential equations and finite state machine is a pest of a pest of a pest of a pest of a problem. Right? So not so good to verify. You can simulate, so you can see how it goes, but to demonstrate that you're never going to have a problem is a very serious point. So, which means that the model is nice, you can do a lot of things, but you have to use it carefully. So, among all the possible hybrid systems, there is one which is absolutely simple and is actually in between in complexity. You don't have to say, I don't know what happens. You can say what happens. It's very complicated, but you can say what happens. And these are called timed automata. Now, timed automata are the only differential equation that goes on is the advancement of time. So instead of having a discrete counter, you have t dot equal to 1, right? T dot equal to 1 is simply a straight line, right? And is the passing of time. That's it. Well, you look at it and say, okay, if I look from a theoretical point of view, there is not much difference, still a differential equation. So this problem may be undecidable. Wrong, it is decidable, and actually there is a transformation that takes this timed automata into normal automata. It has a gazillion state, but still finite. Okay, so that's a nice thing. That's the reason why I say it is in between. And so in this particular case, there is a continuous variable. The inputs are click, single, double. This is the click of the mouse. And so when you want to move the cursor, you say mouse up, mouse down. So this is the finite state machine that is describing this. And there is x dot t equal to 1 is essentially the fact that there is time goes by. So, okay, this simple form of hybrid system is called a timing automata, where dynamic is just passing of time. Okay, big deal. But from a theoretical point of view, the two guys who discovered this timed automata, one was a professor here, Tom Hansinger, and another one was Rajiv Allur from University of Pennsylvania, made a fortune, academic fortune, not $1 gazillion a la, Bill Gates, but they made a fortune in the sense that this was a very nice theoretical result to show that this differential equation are easily handled with this system, this hybrid system. So how many states does this automaton have? This is the great result of Hansinger and Allur and Dill, actually there's a guy from Stanford. Okay, so this results actually says that there is an equivalent finite state system that describes the stuff. Now, if you want to challenge yourself, try. Actually, the idea was very simple, but the whole point is like the Columbus egg, right? Once you want to make the egg stand up, you just click, put it there, stands up, right? So there is a very simple trick that these guys did, and that could make that true. So now this one is hybrid automata of a traffic light controller, where you have x dot t equal to 1, which simply says that time is passing. You eliminate the counter and you put x dot t equal to 1. It doesn't change anything, essentially. But that is the same representation as before. Now, though, is done with a time automata. So there is a timer, for example, that you can use this thing. How would you model a timer that generates a tick each time t time unit elapses? That you can do it with a hybrid system. You have x dot t equal to 1, so it goes like this. When it hits a threshold, ka-chonk, resets and does a tick. So the actual movement in dynamic space goes like this, tung, 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 tung. And the change of state corresponds to a discontinuity in the solution of a differential equation. Because when you go here, it's reset, you go here, starts again. Tick, goes down. Tick, goes down. Okay? So that is essentially what it is. So you have a self loop. You have st larger than or equal to t. You output tick. Otherwise, you set st equal to 0. Okay? That's it. Very simple. So a similar timing automata can model a generator of a timer interrupt. So you have seen the interrupts mechanism in your labs, and you can you can have a generator of interrupts using this mechanism of counting time. Now, this one is the other example in which you can use hybrid automaton. What you see there is a bouncing ball, and the change of state is when it hits the ground and changes direction. So you can say ordinary differential equation moves down, ka-chonk, change state, ordinary differential equation goes up this way. Okay? Then it reaches that center and goes down, so at this point changes again, changes state, and going down. So the states are going down, going up, and there are 2 points. I hit the ground, and I hit the topmost center. Okay, so that's it. So it's the same thing as we saw before, except that this is again, given that the mass is always the same, there is no input, and so on and so forth, this can be modeled as a timed automaton. So what you will look like, you see the ting-tang, 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 which is the velocity, the speed, as this discontinuity, which corresponds to the two topmost position of the ball and when it hits the ground. Okay? So notice that if you want to plot the trajectories of the hybrid system, every time you change state, you have a discontinuity. Right? You may have a discontinuity in the variable themselves, in their derivatives, but there is always a discontinuity because it's discrete change of mode. Okay. So, and again, this when-do reaction occur in hybrid automaton is when the ordinary differential equation hit the boundary and then you change the mode of operation. So occur continually with a continuous state variable being continually updated. When it reaches a particular threshold, you change condition. So now suppose x and y are discrete and pure signal. When does this transition occur? At this point, since you have the advancement of time embedded in the model, then you can say that the earliest time t when x is absent after entering S1, this will be the same time when S1 is entered. You can, as an exercise, decide why is the case. If x is absent when S1 is entered, then the transition is taken at that time. If x is present when S1 is entered, then it will be absent at time infinitesimally larger. And so introducing the notion of time, you can make that in contradiction that we had when we had everything discrete go away, if you want to, right? Because this is more physical phenomena by introducing these delays. Essentially what you are doing is that you are introducing the concept of a delay. Okay, that's it. So I'll see you next week.